How do sidebands form during analog modulation? Imagine you're at a lively concert where different instruments blend to create a rich sound. In the world of electrical signals, a similar process happens when a carrier wave mixes with a message signal. When we talk about analog modulation, this blending produces new frequencies called sidebands. These sidebands are essential because they carry the actual information we want to transmit. Let's start with amplitude modulation, which is one of the simplest forms. Here, the amplitude of a high-frequency carrier wave changes in proportion to a lower-frequency message signal. Think of the carrier as a steady drumbeat, and the message as a singer adding variations to the volume. When you change the amplitude of the carrier based on the message, the overall signal's spectrum shifts. This shift results into new frequency components, one slightly above the carrier frequency and one slightly below. These are the upper and lower sidebands. They contain all the information from the message signal. The carrier itself acts like a carrier wave, helping the receiver identify and demodulate the signal, but it doesn't carry the message directly. Now, how do these sidebands actually form? It all comes down to the math behind the signals. When you multiply the carrier wave with the message signal in the time domain, it corresponds to a process called convolution in the frequency domain. This convolution shifts the baseband signal's spectrum to be centered around the carrier frequency, creating the sidebands. The result is a spectrum with the carrier in the middle and the sidebands spaced evenly on either side. In frequency modulation, the process is a bit different. Instead of changing the amplitude, the frequency of the carrier varies according to the message signal. This produces a series of sidebands spaced at multiples of the message frequency away from the carrier. The number and strength of these sidebands depend on the modulation index, which measures how much the frequency is varied. Because of this, frequency modulation produces many sidebands, making the overall bandwidth much wider than amplitude modulation. There are also variations designed to make better use of the spectrum. For example, in double sideband suppressed carrier modulation, the carrier is removed, leaving only the sidebands. This saves power and bandwidth. Single sideband modulation takes it a step further by transmitting only one sideband, either upper or lower, which halves the bandwidth needed. Understanding how sidebands form helps in designing efficient communication systems. It allows engineers to optimize how signals are transmitted, ensuring they use the available spectrum wisely while maintaining signal quality. Sidebands are the frequency-shifted copies of the original message, enabling high-frequency carriers to carry low-frequency information over long distances.